You can see this figure here is a three-state Markov model for EI system with hard standby, which is a randomly changing dynamic system. The Markov model consists of states and the transitions, the interstate transitions here, shown here, and here, and here, and the transition rates, which are labeled on the top of each transition. Like here you have 2 lambda, here you have lambda, here you have mu system repair, and here you have mu shutdown repair, and here you have lambda common mode. Let me explain state after state and then the transitions between them. So let me start with state 1. While in state 1, it is a normal state or the fully operational state where system A and system B are working, and it is also the initial state. So while in state 1, based on the internal diagnostics coverage, in the event of safe detected failure of a system A or system B, a transition occurs from state 1 to state 2. This is a transition occurs. The transition is shown with the arrow towards the state 2. The transition occurs from state 1 to state 2. So it is switching from main system to standby system, which is automatic. There is no manual intervention. And the failure rate is 2 lambda. That is the transition rate labeled on the top of transition is 2 lambda, where lambda is the failure rate of a system A or system B. The state 1, in the event of safe detected common mode failure, that is both system A and system B have a that is system A and system B have a common mode failure. Then there is a transition from state 1 to state 3 through this transition shown with arrow towards state 3 with a transition rate lambda common mode. So if there is a common mode failure, that comes to state 3. Similarly, from state 1, it comes to state 2 in the event of a failure of a system A or B. Now, in the standby state, in the standby system will first attempt to recover the failed system. That is a failed main system. Either it could be system A or system B. And this the recovery process, that is a mu system repair here, has 3 components: mu1, mu2, and so the standby system will first attempt mu1, that is auto reset. So standby system will attempt auto reset on the failed system. In case the auto reset is successful, then it moves from standby to main system through mu1, through mu1, which is the auto reset recovery rate of the system of a failed system, either it is A or C. So if the auto reset is successful, then it jumps from state 2 to state 1 through this transition with the arrow shown towards 1. If the auto reset fails, then the standby system will attempt minor repair. So it informs the station master. It gives alert to station master. Station master will inform the ESM. The ESM will come to the site, and he repairs the system, failed system A, and by replacing the faulty card, say, and then the system is restored. And once the system is restored after the minor repair, then it moves from state 2 to state 1. In the event that is through mu2, it moves from state 2 to state 1. If the minor repair also fails, then standby system will attempt major repair. So it gives alert for major repair, and the DSM and the AMC representative is called, and the recovery for major repair rate of a system as per the major repair rate of the system mu3, it moves from state 2 to after the major repair by the AMC representative. So that is how the mu system repair is shown as mu1 plus mu2 plus. Similarly, while in standby uh, before the system repair, that is system A is still not repaired, then if there is a save detected failure in the standby system itself, then it will jump from state 2 to state 3 through this transition arrow towards towards state 3 with a transition rate lambda. That is failure rate of standby system, and it goes to state 3. From the so in state 3, where both the systems are down, as alert is given to station master for shutdown for the shutdown repair, and the AMC person comes to the site and he will repair uh, in a given time, whatever 4 hours on average. And then after the system repair, a transition occurs back from system 3 and so a transition from state 3, that is on the shutdown state to state 1. That is after the shutdown repair, the systems are restored and the transition occurs from state 3 to state 1. In that way, based on the random events of failures and on repair, the Markov model will move from state to state. In the next slide, we would further explain, on this, what are the practical values taken for lambdas and mu's, and what is the role of transition rate. These aspects will be described in more detail in the next slide. In continuation with the earlier slide, we explain the transition rates of three-state Markov model. We give the explanation of transition rate of three-state Markov model. The transition rates are 2 lambda here, here. There is from outgoing transitions of state. All outgoing transitions of state are described by the transition rate with a label on the transition. Like from state 1, you have 2 outgoing transitions, state 1 to 2, it is 2 lambda, another outgoing transition from state 1 to 3, it is lambda common mode. Similarly, in the standby state, you have 2 outgoing transitions, one from state 2 to state 1, that is this, mu1 plus mu2 plus mu3, system repair. And similarly, from state 2 to state 3, you have the transition has a transition rate lambda. Similarly, shutdown rate also, there is a from state 3 to state. So there is outgoing transition of state 3. Then you have a transition rate associated with that. You can see for example, you take lambda, which is failure rate of a system, A or B, that is equal to 1 in 3 months. And we assume that the failure rates are same. Now here, I want to explain how this 2 lambda has come, the transition between 1 and 2. The 2 lambda has come because there are 2 systems in A and B. There are 2 systems in state 1, fully operational state. There is system A and system B, and any one can fail. Like I give an example, lambda 1. Let's take this figure. So you have state 1 and state 2. There are 2 transitions, that is lambda 1 and lambda 2 between the same states. Like if you let us say the failure rates of system A are different from the failure rate of system B, then you have if lambda 1 is the failure rate of system A, then lambda 2 is the failure rate of system B. Then this state, the transition between 1 and 2, it will become 1 and 2 will become lambda 1 plus lambda 2. This is like the transition rates are added. One lambda 1 and lambda 2. And then you have lambda 1 and lambda 2. Because lambda 1 is equal to lambda 2 is equal to lambda, therefore you have 1 and 2. The transition rate between 1 and 2 equal to 2 lambda. 1 and 2 equal to 2 lambda because the failure rates of system A and B. Similarly, if you see the recovery rate from state 2, as I explained before, the standard system will try to first recover, restore this failed system. So it takes 3 steps. First is auto reset recovery, mu auto reset recovery, which is I assumed as 10 seconds, which translate to 360 per hour. Just as the failure rate as assumed 1 in 3 months, that is equal to 1 by 3 into 24 into 30, which is so much per hour, 0.0004. So in this way, the minor repair mu is the minor repair rate, which is 2 per hour, major repair rate, which is 0.25 per hour. So the standby state will try various options, mu1 for recovery. If that fails, then mu2 minor repair for recovery. If that fails, mu3 for recovery. So basically 2 and 1 transitions, it should have 3 transitions like this. Between 1 and 2, you have 2 transitions. You will, between 2 and 1, there will be 3 transitions of mu1, mu2, and mu3. So I've added, just as I've added these 2 transitions here. Similarly, I'll add all the 3 recovery rates, 3 mu, to make mu1 plus mu2 plus mu3, which constitutes the mu system repair. So in this way, we make the transitions. Transition rates are key in the for the in the stochastic model, which I'm going to describe in the next. Transition rates, this and this, are failure rates and recovery rates, which govern length of time that elapses before the system moves from state 1, from the originating state to the target state of the transition. And that time, that is the state holding time. So the state holding time here is governed by the outgoing transition rate, 2 lambda, and based on the 2 lambda, it stays in the time. The state holding time takes the value based on the transition rate, governed by the transition rate, and the state holding time is the key. And this will help us in the computation. The state holding time, which is governed by the outgoing transitions, will help us in our objective of computation of probabilities of being in each state after a time t, which could be 1 year or 6 months or 2 years, which helps us in the investigations, in the reliability investigations. The failure rate here, whatever we assumed here, the failure rate of one system, the common mode failure rate, auto reset rate, minor repair rate, major repair rate, shutdown rate, are all based on the field data from the inputs from the field. In this slide, we describe the stochastic Markov process, which is the essential component of Markov. You can see that the system enters state 1, that is the initial state, as we can see the initial condition, and it spends an amount of time called the holding time. In this case, in state 1, the state holding time is T1. It spends some time in T1. It starts from state 1 because the initial condition, there is probability of 0 of state 1 is 1 and the probability of being in other states 0. Therefore, it begins with state 1 as per the initial condition and it stays until state holding time T1. So the system enters state 1, spends an amount of time equal to T1, the state holding time T1, which is a continuous time random variable, and then jumps to another state. That is, it jumps to state 2, and it stays spends an amount of time in state 2, which is state holding time T2, then jumps to another further to another state, that is, it jumps to T3, where it stays for some time until it reaches the state holding time of that state, that is T3, and then spends time in another state. Then it comes back to state and it jumps from state 3 to state 1 and spends another holding time and then jumps to another state. It can go back to the same state also. So it jumps to the another state and so on. This process, this stochastic process for jumping from one state to another state, based on the state holding time in each state, is called the Markov process. As you can see, that each state has a Markov as a state holding time. The state holding, you can see that the T1, T2, T3 are the continuous time random variables which changes with time and which have exponential distribution. T1 is state holding time. You can see that the state holding time T1 is the exponential of outgoing transitions of state. So T1 is a continuous time variable with probability distribution, with exponential probability distribution. You can see this. This is exponential holding time is a exponential probability distribution with the outgoing transition with the transition rates of the outgoing transitions as parameters for the exponential. Like for example here, the state holding time. So you have two outgoing transitions from state 1 to state 2, that is here, and then you have from state 1 to state 3 another transition. The parameter of the first transition is 2 lambda, and the parameter of the second outgoing transition is lambda common mode. So T1 is equal to exponential of 2 lambda plus lambda common mode. So it stays here, system the Markov process stays here, and based on the exponential distribution of the parameter, so it 2 lambda now and lambda common mode. It takes the minimum of the two. That is, the exponential value of 2 lambda is considered, and the exponential value of lambda common mode is considered, and whichever is less, the holding time will, the holding time set to whatever is less. So these are called this is called competing exponentials. There is case of competing exponentials. So T1 equal to exp of 2 lambda and lambda common mode, which are competing exponentials, and the holding time will take the minimum of the competing exponential and accordingly make a transition. If the exponential of 2 lambda is less than the exponential of lambda common mode, then T1 will be equal to exponential of 2 lambda, and so the system makes a transition from 1 to 2. Similarly, in T2, there is competing exponentials. You have exponential of lambda and plus mu system recovery. So there are two outgoing transitions, one here, one from 2 to 1, another from 2 to 3. So again, whichever is less, whichever is the minimum of the two competing exponentials, the state holding time will take that, and then as soon as that state holding time is reached, then it jumps to that particular through that particular transition through that with that parameter of the transition. It goes from state 2 to state 3. If exponential of lambda is less than the exponential of new system repair, then it goes from state 2 to state 1. But if exponential of system repair is less than the exponential of uh, uh, lambda, that is the failure rate of system, then it moves to. So in this way, the Markov process moves from state to state, and the state holding time will give the probability of being in each state, because the probability of each state will change with time, and because it depends on the exponential value of the outgoing transition, which is a random variable, so it changes with time, and so the probability is also one change. Now, what we are interested is a transient solution and a steady state solution. In the transient solution, what we are interested is for a given time t. That this process, the migration of this process, from state to state, uh, for a given time t, uh, is of consequence, as we are interested in the probabilities being in each state at the end of time t. So the transient solution of the Markov model will help us to find out the probability distribution at the end of time t. From the probability distribution, that is the probability of being in each state at the end of given time t, we can find out the reliability. We can obtain the reliability and ability. In the case of steady state, the changes in the probabilities in each state will not change. They'll be constant, and uh, they remain stationary. So in steady state, this Markov process will move from state to state and migrates. The probabilities also change, but finally they reach a steady state, that is with the stationary distribution. Under the as per the stationary distribution, we get the probabilities of being in each state, and from there we get the reliability and availability. This is how. This is the intuitive explanation of the Markov process. In the next slides, we actually see how we compute them with the help of matrices. Elements of state transition rate matrix Q for the case study. The three-state transition diagram is shown below. The matrix Q is an array of numbers which describe the rate at which the Markov model transition between states occur. You can see that the transition between state 1 and state 2 is 2 lambda. The transition rate between state 1 and state 2 is 2 lambda. As you can see here, state 1 and state 2 is 2 lambda. Similarly, the transition rate between state 1 and state 3 is lambda common mode, which is shown here. We also see the condition that the sum of the numbers in each row in Q has to be 0. So this 2 lambda plus lambda common mode you take the, you add the both and give a negative sign here that is given in the diagonal, that is in the first element. And so if you add all these elements, it will come to 0. In this way, um, we set the state transition rate matrix Q. Ambient solution for the case study of three-state Markov model given at figure 1. We know that the solution for the Markov model is P of t equal to P of 0 multiplied by e to the power of qt, where is equation 1, where pt is the state, is a transition probability matrix, and the initial conditions is 1 0 0. That is the Markov system, the Markov process is in initial state. 1 are the initial conditions, and Q is the numerical state transition rate matrix of three-state Markov model given in the previous slide. T is the time t, that is 1 year. Substituting the above values in above equation 1, these values, we substitute these values, we get probability of t at the end of 1 year equal to 0.9997575, and that is probability of being in state 1 when it is normal. Probability of being in shutdown, no, a probability of being in standby is 500025391, and probability of being in shutdown is 0.0023995. From this, we know that the system reliability is equal to the probability of being in state 1, which is 0.39 followed by 75753, and then system availability is 0.9997625. In this slide, we give the impact on system reliability with variation of failure rate of a system. We also give the impact of system reliability with changes, variation in the repair rate of system shutdown. We can see this is also called a sensitivity analysis. Now we can see that the impact of system reliability with changes in the failure rate of a system is less than the impact on system reliability with changes in the recovery rate of system shutdown. In this slide, we obtain the steady state solution of the Markov model, three-state Markov model, where pi 1 to pi 3 are the steady state probabilities, the state probabilities being in states 1 to 3 respectively. And we have equations pi 1 plus pi 2 plus pi equal to 1, pi q equal to 0. Solving these two above equations, we get pi 1, pi 2, pi 3. We got pi 1, pi 2, pi 3, and from there we get reliability pi 1 is equal to 0.96984, and availability is equal to 0.9971. So this we get the reliability and availability. You can see that the impact of changes in on the failure rate of system on the reliability is less than the impact of change the rate of system shutdown. Change reliability is system reliability at the end of using, which is 1 year of operation. You can see it. In this way, we see that uh, when when we're changing the values of only one parameter, this sensitivity analysis is only for change of one parameter, that is at a time, failure rate of one system, failure rate of, and failure rate of shutdown. It's not for changing both the parameters. This does not. It is only a sensitivity analysis per parameter for a change. So the impact of change in shutdown rate, that is major repair rate, is more than the impact of change in failure rate of a. This slide gives analysis of results of steady state solution through migration of probabilities. The Markov model of system will contain a single initial state which represents fully operational system. In this case, it represents state 1. The initial condition is given here. The probability of being in state 1 is 1 in the initial state, and the probability of being in state 2 and state 3 is 0, 0. Now, from this initial condition, as time progresses, the probability migrates from the initial state to other states of the model based on the Markov process, which moves from state to state uh, based on state holding time, which is a random continuous time random variable with exponential probability distribution, which was explained in the earlier. So the probability migrates from the initial state to other states through the transitions. Through the transitions, it moves from one state. The probability moves from one state to another state to here through the transitions at a rate determined by the transition rates labeled here. Lambda is one rate, transition rate. Lambda is another transition rate. Lambda shutdown is another transition rate. So let us say, for example, if you see the failure rates here, if you look at this table here, you can see that the failure rates here, lambda equal to 0.0046, and for the processor, for system failure, failure of a system, and a common mode failure when both the system A and system B fail, are very low. System failure of lambda is 0.0046, common mode failure at 406. Whereas the recovery rates are, mu1, mu2, mu3, mu shutdown repair, they are very. So with the result, the states on the left, is, the probability will migrate to the states on the left because the failure rates are uh, are low. The movement to the right are low, whereas recovery rates are very fast. So probability will probability of migrating to states on the left will be more than the probability of uh, moving to the states on the right. For example, from the fully operational state, if there's a failure, it goes to state 2. But because of the very fast recovery rates, it quickly comes back to state 1. So in that way, the transition in that way, based on the data you have, the failure rates and the recovery rates, the probabilities will change from state to state. So eventually, it will come to steady state where it will come to steady state, that is pi 1, pi 2, pi 3, where the probabilities don't change. The probabilities assume a stationary distribution. Therefore, at steady state, the probabilities of the stationary distribution is defined as pi 1, pi 2, pi 3, where pi 1, pi 2, pi 3 are steady state probabilities of being in 1, 2, 3. So from the initial condition 1, 0, 0, the probabilities will migrate to different states based on the state holding time, which is a random variable, and eventually it reaches steady state. So at steady state, we have the system reliability, the probability of being in state 1, and system availability, probability in being in state 1 and state 2. So that is how you explain these values here. Very high values, as you see, because the failure rates are very low and the recovery rates are very fast. In this way, we analyze this slide gives the expansion of three-state Markov model, which we have described as a case study, with the addition of an unsafe state. Like you have three states here, and we are adding an unsafe state, state 4. So in the event of an unsafe failure, then there is a transition from state 2 to state 4 with a transition rate lambda THR, which is the threshold hazard rate for SIL4 equipment, which is 10 to the power minus 9 per hour. Similarly, from state 1 also, there can be a transition based on the threshold hazard rate for SIL4 from state 1 to the unsafe state. And once they reach the unsafe state, there are no outgoing transitions from state 4. There are no, you can see that there is no outgoing transition from state 4, and that state 4 is called the absorbed state. So in this way, we can expand the three-state Markov model. This is another example of expansion of three-state Markov model to six states. Now, we are partitioning the six states into internal states, which are inside the system, and external states, which are for external actors, that is for SM, ESM, AMC representative, and also for ES. So we have added extra states. We have expanded it to know how to model the external actors, that is station master, ESM, and AMC. We are modeling it with external states for external actors for repair and restoration. We can also see that in the internal state, there is auto reset recovery. See, from state to standby to standby. As we have discussed before, through auto reset, the standby system can restore the failed system, failed main system. So mu is the auto reset recovery, which is automatic. So that is how it is. That is how this we can model the internal states as well as the external states and find out the probability of being in each state. That way, it will help the administration to quantify what is the reliability and availability. The only thing is that these failure rates have to be correct. Like lambda alert 1 is one failure rate, lambda alert 2 is alert 1, alert rate, and lambda alert 2 is another alert rate, then lambda minor failure, lambda shutdown, and then recovery, mu1 and mu2. So in this way, we can model the external state. Main thing, the accuracy depends on the failure rates and the recovery rates. As you can see, a model is an approximation. Is an approximation. The accuracy of results depends on the assumptions of failure and also on the matrix condition for matrix. If the data is accuracy of field data is not there, then results also is not there. We are assuming that the failure rate, repair rate are constant, which in practice may vary with season. In the rainy season, failure rates may be more. Inter-arrival failure repair recovery rates are assumed to have exponential distribution, which may not be true in practice. The failure rate may not be constant, so the exponential probability distribution may not may not be applicable. In this way, these are some of the limitations of Markov. Philosophy of life in Markov model. State of mind should always depend on the present state of life and not on past states of lives and not on how we have arrived at the present state. The difficulty, it is difficult to follow in real life with the society around.